Howdy everyone, welcome back for Chapter 15 example problems. Here we'll be looking at equilibrium equations and how they will work in a little more technical standpoint than just products over reactants, but what can we do to manipulate them, to combine them, to work with them. So here we go. We'll start out with manipulating the equilibrium constant. What happens to the value of K when we change a reaction direction, or if we combine reactions, how do we do that? So here we have this problem where two equations are given and they each have an equilibrium constant. Great. And they want us to find out what would this equilibrium constant be if we combine those two equations into this overall reaction there. So this is going to be very much like a Hess's law problem from chapter 5, where we say, okay, let's look, what do we need as a reactant, what do we need as a product, do we have to flip a reaction around, do we have to double it, anything like that. And when we do that, then we'll add them all up at the end. We'll combine the K's and get our final answer. So for this one, we can look and say, okay, I need hydrogen as a reactant. I look up here, I only see hydrogen in one equation, the first one. It is a reactant, so that's a pretty good clue. Keep that equation the same. So COO plus H2 is in equilibrium with cobalt and water, and that also gives me water as a product, so that's a good sign. Now for the next thing, I want carbon dioxide as a reactant. When I look up here, I see it in the second equation, but it's a product, so I'm going to have to reverse that equation. Right? So that will make CO2 the reactant, and also plus cobalt in equilibrium now with cobalt oxide and carbon monoxide. And now, okay, carbon monoxide is listed as a product. I wanted that as a product, so that also worked out, so that's great. So now we say, okay, well, what did this do to our K values? Well, when we looked at this first one, we didn't do anything to it, so K stays the same. So I'm going to call this K1. It'll still equal 67. But the second equation, we reversed it. And so if we think of K normally being products over reactants, if we write the reaction backwards, it's now reactants over products. It's the reciprocal. So this K is now going to be the reciprocal of what it was. It's going to be 1 over 490. Right? And now we say, okay, let's combine those two up. Let's make sure it works right. So cobalt oxide I see is going to cross out. Cobalt's going to cross out. So if we just add this up, we'll have the H2 plus the carbon dioxide going to the carbon monoxide and water, just like we want in the given. When we combine equilibrium reactions, the products of the first one become the reactants of the second. The way to cancel them out is to multiply. We multiply these together. So our overall Kc is going to be K1 times K2. So in this case, that'll be 67 times 1 over 490. And if we punch that in, we will get that equals 0.14 with 2 sig figs, it's like 1367. But that's our final answer there. And so we say, okay, it's less than 1. That means this reaction will not favor the overall products. It'll favor the reactants because it's less than 1. It's because, when we reverse the second one, we got a real small equilibrium there. That one's going to favor reactants a lot for that step. All right, so that's how you can manipulate the equilibrium constants. If you reverse a reaction, it becomes the reciprocal. If you double a reaction to make balancing work out, then you square it because, it would be K1 times K1 again. So, K1 squared. You can think of it that way. All right, let's move on then to a ice table problem. This is 1537. They tell us we've got a mixture with 3 gases, some carbon dioxide, some hydrogen, and some water. It's in a 2-liter vessel. Always look out for that because that can be a trick sometimes that they don't give you a 1-liter vessel. Here it is. It's the same reaction. This is called the water-gas shift reaction because we make water and we shift the oxygen, whatever. They want us first calculate the initial partial pressures. We would have to do this anyway to get some equilibrium stuff. For some reason this didn't say it because I know I just edited it from a previous typo. This was at 500 Kelvin because that's going to be necessary. To get the partial pressures, we use the ideal gas law that PV equals nRT. So in this case, the pressure will equal nRT all over the volume, so that's why we needed that 2 liters. So when we plug this in for the various gases, I'm going to be a little bit lazy and leave off units. For the carbon dioxide, it's 0.20 moles times 0.08206 liter ATM over mole Kelvin. For the temperature, we said it's 500 Kelvin. Don't know why that got cut off. Maybe it's on the next slide. For over the volume, over 2 liters. And so if we plug that in, 0.2 times 0.08206 times 500 Kelvin divided by 2. So for carbon dioxide, we get 4. How many sig figs? 2 sig figs. 4.1 ATM as its partial pressure. We would do the same thing for the other 2 gases. We would just change this first number. So for hydrogen, if we plug in 0.1, well, it'll be half that. So it would be what, 2.1, probably with rounding. Let's double check that because I just cleared out my calculator, of course. Times 500 divided by 2. Yeah, it's 2.05, so that would be 2.1 ATM with sig figs, and then with the water, that would be times 1.6. That would be 3.3 ATM. So we have those. Now, if you wanted to keep some extra decimals around for later on, it might make some later answers a little better, but officially this is what we should have. All right, so we'll keep those numbers in mind. I'm going to write them up here again. CO2 was 4.1. This was all initial. Hydrogen was 2.1. And the water, I've already forgotten, was 3.3. Okay, ATM. All right, so we've got that same setup. Okay, here it is, yeah, at 500K, great. At equilibrium, the pressure of water is 3.51 ATM. Calculate the partial pressures for the other 3. Okay, so that means we got to make our ice table. So again, I like to rewrite the equation so I kind of have columns for all my chemicals. And then we'll make our table. Three columns because we're going to have the initial, the change, and the equilibrium value for each. We'll make our columns. And so we can plug in our initials. Carbon dioxide was 4.1. Hydrogen was 2.1. Water was 3.3. And because nothing was given there, okay, carbon monoxide must have been 0. It wasn't mentioned. The only one they give us is that water is 3.51 at equilibrium. But that allows us to say, oh, this is going to be a plus X because it's one product. This is one product. It's a plus X. These two are reactants. It's 1 and 1 for both. So it's just minus X and minus X. So remember, if there's balancing, then it would be 2X if it were 2 or 3X if it were 3 of something. Here it's 1, 1, 1, 1. So it's just minus 1X, minus 1X, plus 1X, plus 1X. All right, but it went up, so it's plus X. We can then solve and say, well, hey, X must be 0.21 ATM. So here I'm kind of wishing we had kept it, the extra decimals. Oh well. So we can plug that in. This is going to be plus 0.21. This will be minus 0.21 minus 0.21. So this will be 0.21. This will be 1.89. We'll leave off the, or don't worry about sig figs too much here. And then this will be, what, 3.89, looks like. Okay, and that's ATM for each. That's part B. So the key was use the one connection you could get and then apply the balancing for all the other changes. All right, now that we've got those numbers, part C, they want us to calculate Kp for this equation. And so Kp is products over reactants. So in this case, it's the partial pressure of carbon monoxide times the partial pressure of water over the partial pressure of carbon dioxide and over the partial pressure of hydrogen, right? So it's still products over reactants. All right? And in this case, we say, okay, let's plug in those numbers. So if we go back and check, All right, so it's 0.21 and 3.51 on top. And for CO2 and hydrogen, it was 3.89 and 1.89. So we'll go ahead and plug that in. 0.21 times 3.51 divided by 3.89 and divided by 1.89, and we get an answer of 0.10. And that seems reasonable because if you remember, this is the same equilibrium as the first one we did combining, but it's at a different temperature. I think the other one was officially at 298 or something else like that. So in this case, with a different temperature, K can change, and it did change, but yeah, it's still in the same ballpark. We went from 0.14 to 0.10. That tells me that, yeah, this is a reasonable answer there. It still favors reactants. Now for the next one, we want to be able to solve for Kc. One moment. Okay, so for the next bit, we're going to calculate Kc. And the trick for this one is, and I'm not going to expect you to memorize this equation, but it is one useful to know from the book, that Kp is equal to Kc times RT raised to the delta N power. And this is where we said the delta N is the change in the number of moles of gas. And so in this case, if we want to solve for Kc, okay, rearrange Kc is equal to Kp now divided by RT raised to the delta N. And I haven't plugged in any numbers yet because for this equation, we don't have to. If we look, we say how many gases do we start with? Not the numbers, but how many moles of gas in the balanced equation. Here it's 1 and 1, so 2 reactants. They're both gases. Here in the products, it's 1 and 1, so 2 gases. Our delta N is 2 minus 2. It's 0. And so RT raised to the 0 power is 1. That means Kc is equal to Kp divided by 1. Well, that means in this case, it's also equal to 0.10. Now, if it were a different number, if, say, it were somehow 2 moles of water here, then it would be 3 minus 2. This would be raised to the first power, so we would take Kp and divide it by RT and get our answer there. But in this case, hey, gases are equal. That means the equilibrium constants, whichever way we do it, concentration or pressure, they're both going to be equal. All right. The last one here is what happens to an equation with Le Chatelier's principle. If we have an equilibrium already set, already at equilibrium, and we do something to alter it, we add or remove something, we change the temperature, we add a catalyst, we somehow change the partial pressures, what's going to happen? And so it's either going to shift right towards more products or shift left towards more reactants based on what will undo the change we made. So here in letter A, if we say we add O2, so here's O2, it's a reactant, and I'm just going to put a little plus sign there. Well, if I add more on the left side of the arrow, to undo it, I need to get more on the right-hand side. So how adding oxygen affect it? That's going to make it shift to the right. It'll make it shift to make more products. All right. Letter B is what happens if I heat the mixture? Well, I got to figure out where's heat, and that's what this delta H information is for. It tells me that delta H is less than 0. Delta H is negative. We have to remember a negative delta H means it's exothermic. Heat is released as part of the reaction. Heat can be treated as a product. So I'm going to write right here plus heat. That heat is as if I'm making, I make 2 SO3s and I make some heat. In that case, if I heat the mixture and increase this amount, while I'm adding more stuff on the right-hand side of the equilibrium, to undo it, I'm going to have to shift back to the left side. So shift left for that one. All right. Letter C, we double the reaction vessel volume. That means all the amounts of chemicals stay the same, but we've increased the volume. That means we have decreased the partial pressures of each gas. And so in that case, we say, well, how many gases are on each side? So we'll say 3 gases of reactants, right? Versus just 2 gases of products. We only care about gases. If something was solid, liquid, or aqueous, ignore it. But we apply balancing, we add that up. And so if we double the reaction volume, that means we dropped pressure for each of them. To undo a drop in pressure, we want more moles of gas. And so we said, well, which side has more moles of gas? The reactant side. So as we increase the volume, we decrease the partial pressures. That means the reaction will shift to the left to try to make more gases, because there's more there on that side. All right. There's a couple more here. Letter D says, what happens if we add a catalyst? This is a definition from the textbook. The key is when you add a catalyst, everything goes faster, but it just goes faster to where it was going anyway. So there's no shift in the reaction. It's just faster, right? So you don't even have to say that. They'd say, how will it affect? It won't. It's just going to stay the same. It'll just get there faster. All right. Letter E says, what happens if we add a noble gas, maybe neon, argon, helium, whatever, add a noble gas to increase the total pressure? Well, this is where people get tripped up because they'll say, oh, we've increased pressure, favor the side with fewer gases. But that's only if we increase all the partial pressures. If we add a noble gas, we've done nothing to the partial pressure of sulfur dioxide. We've done nothing to the partial pressure of oxygen. We've done nothing to the partial pressure of sulfur trioxide. If we've done nothing to those numbers that are in the KP, then nothing happens. So when we add a noble gas, again, there's no shift. We've increased the total pressure, but there's no shift at all because those pressures didn't change. And then finally, what if we could somehow remove the sulfur trioxide gas? Maybe there's some way to liquefy it. Maybe there's some way to filter it out. But if you remove something, so I'll put a minus there, the reaction is going to try to shift to replace it. So if we take away something on the right, we'll shift to the right to try to replace it. So removing the product will make it shift to the right. All right, so there's some chapter 15 help. I hope this was helpful to you. Again, come in for office hours, see the tutoring center, read your textbook, look at the dynamic study modules, get the help you need. You're even allowed to watch YouTube videos that aren't mine. That's okay. But equilibrium can be tricky, and there's 2 more chapters of it. It's 15, 16, and 17 are all about equilibrium, so there's a lot of stuff we got to get good at, and especially these fundamentals. We got to get good at them. So hopefully this was helpful, and I will see you back for chapter 16.